capacitors can be made with different dielectrics. You can have capacitors with polymer as a dielectric. Polymer has a low dielectric constant, and therefore size of the capacitor will be big. You can make capacitors with a ceramic which is barium titanate, in which some of the barium atoms are replaced with calcium. The barium titanate ceramic will be paraelectric above a certain temperature called the Curie temperature, and below the Curie temperature it will be ferroelectric. In the paraelectric phase, the dielectric constant will be very large, and it will vary as 1 by T minus Tc, where T is the temperature of the dielectric and Tc is the Curie temperature. By adding calcium to barium titanate, we reduce the Curie temperature to a value of about 10 to 20 degrees centigrade. So, at room temperature, these ceramic capacitors are paraelectric with a very large dielectric constant. So, size of the capacitor is small. We can measure the variation of the capacitance with temperature and verify that the dielectric constant varies as 1 by T minus Tc. This is called the Curie Weiss law. So, I have an insert, and again in this is an aluminum block in which there is a hole, and you have put the platinum 100 resistance thermometer to measure the temperature of the block. On one face I have the ceramic capacitor 0.1 microfarad value, and on the other face I have a polymer capacitor with the same value of the capacitance. The leads from the thermometer, ceramic capacitor and polymer capacitor come to this terminal block. The platinum thermometer is connected between the two yellow banana terminals. Between the red and green terminal, here I have connected the polymer capacitor. Between the red and green, here I have connected the ceramic capacitor. The two capacitors will hang in a furnace and the temperature can be changed. Between green and blue, I have 1 K resistor at room temperature. Similarly, between this red and blue, I have 1 K resistor at room temperature. The two reds are shorted and the two blues are shorted. Therefore, this red is shorted to this red, this blue is shorted to this blue. I told you about barium titanate. It is a ferroelectric material. A ferroelectric material is one which has a spontaneous electrical polarization, which can be reversed with an electric field. Such spontaneous polarization is exhibited below a temperature Tc called the Curie temperature. Above Tc, there is no spontaneous polarization and the material is called para-electric. If you take barium titanate, its Curie temperature is 128 degrees centigrade. Above 128 degrees centigrade, it is para-electric. Below 128 degrees, it is ferroelectric. Similarly, potassium dihydrogen phosphate has a Curie temperature minus 151 centigrade below ice point. If the temperature is above minus 151, it is paraelectric. Below minus 151, it is ferroelectric. If you replace barium with calcium, then the Curie temperature comes down. You can reduce it to as low as 20 degrees centigrade or less. In the paraelectric phase, the electric polarization P as a function of the electric field is linear. When you reverse E, the polarization changes sign. In the ferroelectric phase, P versus E shows hysteresis. In the paraelectric phase, T greater than Tc, the polarization is epsilon naught, which is permittivity of free space, into susceptibility chi into electric field. This electrical susceptibility is proportional to 1 by T minus theta, where theta is the temperature close to Tc, and this is called the Curie Weiss law. The dielectric constant of the material is 1 plus chi, but near Tc, chi is very large, and therefore it is almost equal to chi. A ceramic capacitor has a ferroelectric material as the dielectric with a Curie temperature between 10 to 20 degrees. So, the capacitance of a ceramic capacitor is proportional to epsilon and varies as the capacitance is a constant by T minus theta. It decreases rapidly as the temperature is raised. On the other hand, a polymer capacitor has a polymerous dielectric. Its capacitance increases very slightly as the temperature is raised. In this experiment, we measure the capacitance of a ceramic capacitor and a polymer capacitor. Both are mounted on an aluminum block which hangs inside the furnace. The capacitances have a nominal value of 0.1 microfarad at room temperature. There is a platinum 100 resistance thermometer also mounted on the same aluminum block. All leads are brought to the terminal block. We connect a signal generator between the terminal, the red and the black terminals here. Between the red and yellow terminals, between the red and black terminal, red and green terminal, the leads from the capacitor are connected. Between the green and the black terminal, I have a resistance of 1 kilo ohm at room temperature. Similarly, the resistance of the polymer, the leads from the polymer capacitor are connected to the red and green terminals on the other side of the terminal block. Between the green and the blue terminal, I have a resistance of 1 K. The two red terminals are connected together, the two black terminals are connected together. I connect the red and black terminals to a signal generator, and I set the frequency of the signal generator at 1 kilohertz. I set the peak to peak amplitude at 2.8 volts. This corresponds to an RMS amplitude which you can measure between the red and black terminals on the multimeter. It is about 0.97 volts RMS. This voltage is applied to the two capacitor resistance elements in series. It is applied both to the ceramic capacitor and 1K and the polymer capacitor and 1K, because the two sides are connected together, they are in parallel. I can measure the voltage across the capacitor by connecting the multimeter between the red and the green terminals. This voltage is 0.892 volts for the ceramic capacitor. If I take the red lead connected to the black terminal, I get the voltage across 1K resistor, that is 0.372 volts. I can also measure the voltage across the polymer capacitor, that is between the red and red and green terminals of the polymer capacitor, that is 0.831 volts, and the 1K connected to the polymer capacitor, that is 0.51 volts. I close the furnace with a wad of cotton. I connect a power supply to the furnace, set a voltage of about 8 volts and adjust the voltage so that the temperature goes up 1 degree per minute. Then when the temperature is 40, 50, 60, 70, 80 degrees centigrade, I measure the voltage across the polymer capacitor and the voltage across on the right. When the temperature is 35, 45, 55, 65, I do the same measurements on the polymer capacitor. I measure voltage across the polymer capacitor and the voltage across the resistance. I continue doing this till the temperature reaches 100 degrees. From the ratio of the voltage across the resistance to the voltage across the capacitance, this ratio is equal to 2 pi f into capacitance into resistance. So, the capacitance is VR by Vc by 2 pi Fr. I measure VR and Vc, so I know the ratio VR by Vc at any temperature. Frequency is 1 kilohertz and the resistance is 1 kilo, 1000 ohms. So, I can calculate C. I can do this for the polymer capacitor from the ratio VR dash by Vc dash measured on the left arm of my terminal block. So, I have the data here 40, 50, 60, 70, 210. For the ceramic capacitance, Vc is given in column 2, VR is given in column 3. The impedance 2 Vc by Vr into 1K is the impedance Zc. Zc is 1 by 2 pi Fc. So, I get the capacitance Ca in microfarad. You see that the capacitance has a value 0.073 microfarad at 40 degrees centigrade. It comes down to 0.0197 at 110 degrees. So, the ceramic capacitance decreases as the temperature goes up. These are the readings for the polymer capacitor. You see that the capacitance is nearly constant at 0.1 microfarad. It increases slightly as you go to 110 degrees Kelvin. From this capacitance, I calculate the reciprocal 1 by C and I plot 1 by C against the temperature T. You see it is a straight line. The intercept is minus 7 and the slope is 0.521. The straight line shows that the Curie Weiss law is obeyed, and if you divide minus intercept, that means plus 7.03 by 0.521, that is 13.4, that is the Curie temperature theta. So, we verify the Curie Weiss law for the ceramic capacitor and its Curie temperature is 13.4 degrees centigrade. This shows how the capacitance varies with temperature for the ceramic capacitor and how the capacitance varies with temperature for the polymer capacitor. The continuous curve shows the Curie Weiss fit with C naught equal to 1 by slope of the straight line and theta 13.4 degrees. You see that the continuous curve fits the experimental data very well, showing that the capacitance obeys this Curie Weiss equation. It is 1.921 by T minus 13.4 microfarad.